Okay, so no slip problem has two different cases. Case one is when you have a wheel rotating on a fixed surface. So that's case one. For case one, we know that we have a special point, point C. Now we know that point is called instant center. But when we learned that knowledge, we didn't know that point is called instant center. So what do we know about point C under no slip condition, rolling on the fixed surface without slipping? So we know a couple things about that point. Because that's an instant center, what's the definition of instant center? It has zero velocity. That's the first thing you should think of. If that's our instant center, that means VC has zero velocity, 0I plus 0J. That's the first thing about this case one, the contact point. Besides that, do we know anything about acceleration about point C? What's the acceleration about point C? Is point C has zero acceleration because it's instant center, has zero velocity? Another concept to clarify. Velocity and acceleration are two different things. Even now we have zero velocity at point C. That doesn't mean we have zero acceleration at point C. They're totally two different things. So the acceleration at this particular point under case one, rolling without slipping, AC has zero I component. So zero acceleration only on I direction. On J direction, we have omega squared R as J. So that's our case number one. Rolling without slipping. Case number two, I think this is where the most mistakes come from in your homework as far as I can tell. What does case two look like? So case two is when you have a wheel that's rolling on top of a block. That block, it's sliding on a surface with a certain speed. Let's call that AB and AB. Okay. Now let's see this again. Let me ask that question. So for the case number two, we still have that contact point C that between the wheel and that block. Is this point C the instant center of our wheel? That's my question. Is that point C the instant center of this rigid body? Raise your hand if you think that's the instant center of that wheel. For case number two. Raise your hand if you think that's not the instant center. Okay. What's the definition of instant center again? Zero velocity. Does this point have zero velocity? Okay. So remember, case one, case two are kind of like the definitions of maybe something you must remember. Those are two special cases. You must remember what is going on under each case. So VC under case two, velocity equals VB. So it depends on how fast that block B is moving. That's on I direction. On J direction, we have zero. Because that block only moves on I direction, nothing's happening on J direction. The acceleration of that point C, same deal. It has two components. The I components, it's the same as that block B. So AB, I. But for the J components, what is on J components? 0? No. So I have a question mark there. Nobody knows. That's something you may need to find out. You can solve by list of system of equations, but no one knows what is that. We only know that's equals AB. Only know that's under the condition you know what is AB, or the problem is given. If AB, this B is moving at a constant speed, then that's 0. For x velocity at point C, we know VB plus 0J. Okay, those are the 2 cases under rolling without slipping. So make sure you keep those in mind. Whenever a good practice would be, whenever you see something's rolling on top of something, first thing you should think about is, okay, this is a rolling without slipping problem. Then you need to determine, is that case number 1 or case number 2? Once you know the case number, write down those equations as you're given to remind yourself we know those things that we can use later on to solve the problem. Okay, that's the first thing I want to cover. Next thing, let's talk about instant centers. Instant center and how to use instant center. If we have a wheel rolling with no slip. Yeah, this is case number 1 we just mentioned. And the contact point here, point C, is the instant center of this rigid body. Okay, let's label points. Point A, point P, point, maybe let's call this point D. Okay, now I have a couple points. We know point C is the instant center. That's no doubt, it's an instant center. How do we use instant center? Okay, first thing I can use instant center to find out is the direction of velocity of any points on this rigid body. So what is the direction of velocity at point A? What's the direction of velocity at point A? We know the instant center. Can we find out direction of velocity? I want you to sketch that, the direction of velocity at point A. Okay, then use your finger, tell me where is that direction. Okay, good. So the direction of point A is pointing straight to the right. Why is that? Because you can just connect instant center with that point and draw a perpendicular line. That line tells you what's the direction of velocity. Yeah, same deal. Can you find out what's the direction of velocity at point P? Straight up, yes. Same deal. Connect the instant center with that point. Oh, it's not straight up. Not straight up. I was wrong. Connect the point P and your instant center and draw a perpendicular line. What's the direction of point P? There's that angle there. So it's like angle direction. Because this whole wheel is rotating clockwise, so there's only one possibility for direction of P, which is going upward. How about the direction for point D? What's the direction for point D? You can use the same method, right? Connect point D and the instant center and draw a perpendicular line. And now you have the direction. But is that going up or down? That depends on how this rigid body is rotating. This rigid body is rotating clockwise. There's only one possibility for D. D has to go that direction in order for this wheels to go clockwise. Does that make sense? So that's the first function of instant center. We can use instant center to find out the direction of velocity. And also, that's also the drawback of instant center, because keep that in mind, maybe write that on your notes. Instant center only tells you information about velocity. What does that mean? It means it tells you nothing about acceleration. So for example, if we already found the velocity information about point A. Let's write A as a vector. So VA plus 0. Okay. Do you guys have any question? Are you all gray? Can we write the velocity of A as this vector? Why I have 0 on J? Because this is what we found out. Velocity at A must go to the right, straight to the right. Nothing is on the J direction, so 0 on J. We do have that something VA is on I. Okay. Now, what is AA? What is AA? If I want to write out my AA as a vector, can I do this? Oops. Can I do this? Who tells you we have 0 on J? One tells you that. So this is not right. For AA, we know nothing. So we want to make sure A has something on the I direction and A also has something on the Y direction. Do not assume AA should be similar with VA, only has I component. That's a wrong assumption. Same deal for any other points. For example, point P. Same deal, AP should both have X components and Y components. And that's how we use instant center. Another thing is, instant center can exist for any rigid bodies. We talk about we use them a lot in the wheel, but if you see something weird, like this is a rigid body, if this is rigid body is fixed, it's pinpoint at this point C, it can rotate about point C. That's also the instant center of that rigid body. If you want to find out any point direction of any point on that rigid body, use the same method. Find direction of point A, direction of velocity at point A. That's just connect these 2 points and draw a perpendicular line that tells you where's the direction of velocity at that point. Okay. Another application of instant center is it not only tells us the direction of any point on the rigid body, it also tells us the magnitude. In other words, the speed. What is the speed of A, P, or D? So that's from the 6 steps on your chapter 2 for instant centers. We can, whenever you know the instant center, you can find out the speed of any point on that rigid body. In this case, let's do speed of P. So we can find out speed of P. That equals omega times distance R P slash C. Okay, so you can use instant center to find out speed of any point. But here, this guy is the angular velocity, angular speed of your rigid body. What is this guy? RP slash C. P, I understand that's the point P we're talking about. Why here we have point C? Yes. The reason that must be C because it must be the instant center. Must be the instant center for the rigid body that with that omega as angular velocity. So this rigid body you're talking about and this omega for that rigid body, they must be the same rigid body. So they must be on the same rigid body. How to find the distance from point A to point C to point P? Point C to point P. Point C is right here, point P is there. That black line there, it's the distance between them. How to find that distance? Trigonometry, right? You have R squared plus R squared square root. How you find out the distance from P to C. Once you have that distance, you can use omega times that distance. That will tell you what's the speed at point C, at point P. So that's one of the application for instant center. Any questions here? Okay, I saw many mistakes. I think a lot of you knows this is the equation to calculate the speed, but you mess up the distance. You don't know which distance to use. It must be the distance from the instant center of the rigid body to the point, this point, whatever that point, in this case is P. All right. Okay. Any questions on instant center? Okay. All right. Now, how about let's do a practice to identify the location of instant center. In this practice, we have 3 links. Let's call this A, B, C, and D. Both A, B, and C, D are pinpoint. A, B is pinpoint at point A. C, D is pinpoint at pinpoint D. Okay, now you have a couple of minutes, maybe 4 minutes, to find out the instant center for each rigid body. And the second thing to find out is the rotation of each rigid body. Are they counterclockwise or clockwise? The given is the link AB, it's rotating clockwise, counterclockwise. Think about where's the instant center. Instant center for AB and CD are very easy to identify. BC could be a little bit tricky. Okay, where's the instant center for AB? Which point? Point A. That's an easy one. IC, AB. Where's the instant center for CD? Which point? Do we have any question that point D is the instant center for CD? Yeah. As long as if you see it, there's a link or it's a bar that's pinpoint at certain point, that must be the instant center. So if this pinpoint at point D, it can only rotate about point D. Remember that again. Recall yourself. Definition of instant center: zero velocity. Pinpoint at D, zero velocity. Pinpoint at A, zero velocity. Okay, where's the instant center for BC? Is it on the BC or outside the BC? It's outside. Raise your hand if you already find out the instant center for BC. Okay, we have 4, 5. All right, so we have 6 steps that should be on your notes, how to find instant center. So make sure you have cheat sheet. You can write that down on your cheat sheet to help yourself during the exam. But let's do a review together. To find out the instant center, you must find 2 points on that rigid body. You know the direction of velocity. So in this case, point B and point C is on the rigid body BC. And we want to find out where's the direction of velocity at point B and C. We just did practice on that. So at point B, use your finger, tell me what's the direction of velocity. Straight up. How about point C? What's the direction of velocity at point C? Use your finger, show me where's that. Okay, either go that way or that way. We don't know. Because we know the instant center for CD. That's how we find the direction for velocity at point C. Now we know the direction of velocity. We can starting to draw lines that are perpendicular to those velocities. One's there, another one is here. Make sure they're perpendicular. Perpendicular. The intersection right there, it's a IC for BC. Now we find out the instant center for BC. Okay, raise your hand if you want me to repeat this again. Maybe tell you, explain more. So the instant center for BC, it's identified. Great. Now we know all the instant centers. Let's look at, are they counterclockwise or clockwise? Which one is counterclockwise? Which one is clockwise? So AB, no doubt, it's counterclockwise. How about BC? Is BC going clockwise or counterclockwise? Okay, what is instant center again? It's a point that has zero velocity, and it's also the point that the rigid body is rotating about. So this rigid body BC, it's rotating about that point, which is its instant center. So that tells you this BC either going this way, counterclockwise, or going this way, which is clockwise, about that point. But which way? Counterclockwise or clockwise? There's easy way to tell. So let's look at this. Do we know the direction of point B? Yeah, 100%. Point B is going up. Point B is going up that way. Point B is a point on the rigid body BC. And this is the instant center. So one point on that rigid body is going up, and this is the instant center. Can you guess this rigid body BC is going counterclockwise or clockwise? There's only one possibility that rigid body BC is going counterclockwise because that instant center is on the left hand side of that rigid body, and one point on the rigid body is going up, but there's no way for this whole rigid body is going this way because that point is going up, it's kind of drag, this whole rigid body is going up. So if this BC is going up, that's counterclockwise about that instant center. Are we good here? Raise your hand if you think that's pretty straightforward. I can see that. Okay, so once you know the instant center, look at the direction of any point on that rigid body. The definition of instant center is that rigid body, imagine this is my pen. The instant center is the point my pen's rotating about. So my pen can only rotate about that point because that's the instant center. So there's two possibilities. Either go this way, that's counterclockwise, right? There's another possibility is rotating clockwise about the same point. Then let's look. On the at the tip of my pen, that's point B. Point B is going up. If point B is going up, where's my pen's gonna go? Is my pen going to go down? No, there's no way. The only way my pen can go is going up that kind of that direction. If my pen's going up, then that's counterclockwise about that point. That's how I would determine if that going counterclockwise or clockwise. All right. So our BC is going counterclockwise. If BC is going counterclockwise, then what's the rotation, what's the direction of velocity at point C? Is C gonna go up or down? Use your finger, show me. There's only one way. So this is wrong. C can only go that direction. Okay, if C is going that direction, what's the rotation of CD? Counterclockwise or clockwise? That's pretty obvious. CD can only go clockwise. Okay. All right, this is how we find instant center and how we use the instant center. All right. And that's almost about everything for chapter 2. Now let's look at chapter 3. Okay. Okay, so I want to compare chapter 2 and chapter 3. They're very similar, but very different. So what's the first equation we learned in chapter 2? In chapter 2, we learned two equations. One is a velocity equation. Another one is velocity acceleration equation. Let's just use velocity equation here. Remember the equation from chapter 2? That's just VA plus equals VB plus omega. AB equals RA slash B, right? That's a simple equation we learned in chapter 2. What is the equation, velocity equation we learned in chapter 3? In chapter 3, velocity equation, look up your notes or textbook. That's VA equals VB plus VA slash B relative plus omega plus RA slash B. Okay. There's a very significant difference here. They look very similar, right? You have 2 points and you can have an equation like that in chapter 2, an equation like this in chapter 3. But there's a huge difference. Everybody, I want you to pay attention here. Huge difference. The point A and B in chapter 2, what about them? What about the point A and B in chapter 2? So A and B in chapter 2, in that equation, must be what? Same rigid body. Yes. Very important. They must be on the same rigid body. How about point A and B in chapter 3? Yes. In chapter 3, that equation, A and B are on different rigid body. On the different rigid bodies. Now I have a question. What if in chapter 3, this equation, these 2 points are on the same rigid body? What if we pick A and B on the same rigid body? What will happen? You can definitely put A and B on the same rigid body and to use this equation. But what will happen? So that maybe we should go back to the rigid body in chapter 2. So if A and B are on the same rigid body, that means the distance of A and B are fixed. It's fixed. So the distance between A and B would never change. They're on the same rigid body. That's the definition of rigid body. Any 2 points will keep the fixed distance. Okay. If we want to use this equation for the 2 points on the same rigid body, this term VA slash B relative, what is that? If right now, Josh and me, we have the fixed distance, what's the relative velocity between us? If you look at me, I look at you, what's our velocity? 0. We're not moving, we're looking at each other, right? So this term is 0 in that case. If that term is 0, what would you have? You end up with exactly 2 same equations. Okay, that's a main difference. I want you to keep that in mind. That applies for the velocity, also applies for the acceleration. The same deal for acceleration equation. For chapter 3, A and B on the different rigid bodies. In chapter 2, A and B must be on the same rigid body. Another thing, besides A and B, how about omega? In chapter 2, what is that omega AB there? In chapter 2, that equation has an omega AB. That is the omega, that's the omega AB for the rigid body, whereas A and B are on. So that's the same rigid body. Same one for A and B. That's for chapter 2. Now let's look at chapter 3, that equation. What is omega there? What is this omega? So remember here, point A and point B are on two different rigid bodies in chapter 3. Okay, now here's a question. If you want to use omega, should that be the rigid body for A, omega A, or omega B? Have you thought about that? So in chapter 3, omega is the angular velocity of your local coordinate system. So it depends on where you set up your moving coordinate system. It's not just the omega for A or omega for B. It's the omega of your moving coordinate system. Like we have 6 steps in chapter 3. In the first 2 steps, you need to set up where's your moving coordinate system and fixed coordinate system. At that time, you already choose which omega you want to use because you need to put your moving coordinate system either on there, depends on the problem. So that determines what is your omega. The same thing applies for acceleration in chapter 2 and chapter 3. For chapter 2, acceleration, there's alpha term instead of acceleration. That is the acceleration of the rigid body, AB. But in chapter 3, omega, which is the angular acceleration, that's the angular acceleration of your local coordinate system, or its moving coordinate system. For example, in that example we did in chapter 3, we put the moving coordinate system on that fire truck, there's the ladder of that fire truck. So the ladder of the fire truck is rotating at a certain rate. That means our moving coordinate system is also rotating at the same rate. That's our alpha and omega in chapter 3. So those are the main difference between chapter 2 and chapter 3. So be careful when you apply equations. I think that's all we have today. Yeah, if you have more questions, feel free to visit me during my office hours. Once again, exam on Wednesday. Make sure you bring your laptop, computer, or tablets.